Hey everyone, welcome back to Learning to Understand Digital Electronics. So in our last two videos we discussed adders and subtractors. Now these were circuits that we used to help add two binary signals or subtract two binary signals. The problem is when we're working with a computer, let's say, is these signals, if we want to add we need a adder, if we want to subtract we need a subtractor, which means we need two components, which is very inefficient. But an adder-subtractor can allow us to actually use both of these systems in the same circuit. And now the key to this is something that we discussed in our very first video called two's complement. So we're going to start off with a basic adder. This is going to be a 2-bit adder, just for simplicity's sake. Although it can be scaled up to a 4-bit, a 6-bit, however many bits you want. So here's our Cin. I'm going to call this Cin. This is going to be A, 0, B, 0. And this is going to be our sum 1. Our sum 0. This is going to be our C1. This is going to be our B1. This is going to be our A1. This is going to be our sum 1 and our C2. So these are both now full adders. So now this works perfect for addition. But how the hell are we going to make this into subtraction? Well, we need to find a way to turn B, the values of B, into 2's complement. So if I were to make a table now with B, and then if I times it by some magical property X, I need to get the output in 2's. Well, actually, I'm going to need the output in 1's complement, and you'll see why. So, when B is 0, B is 1. When B is 0 and B is 1. So now when we're adding, our output needs to be, 0 and 1, because B needs to remain the same when we're adding. But when we're subtracting, well, B needs to be 1, and 1 needs to be 0. So, if you actually notice this shape, this looks very similar to a gate we have called the exclusive OR. And now, if I plug in the values of x, so if I say x is 0, and 1, 1. Now this looks exactly like the table for exclusive OR gate. And you notice that we can split this table in half. When we're adding, x will be 0. And when we're subtracting, x will be 1. Now, if I were to make x equal to this, if I were to make Ci x, well then we get a magic thing where we actually get our 2's complement, where we add the 1 to the end of the number by making x 1, and then we add it to the system. Now, I get that can be a bit confusing how I just said it. So, let me actually demonstrate this. So B will now be replaced. So B0 and B1 will now be replaced with exclusive OR gates. So this would be 1, and this is B, 0. So this is what our gate looks like now. This is what our adder-subtractor will look like. And to demonstrate the properties of this is we're going to use the value of, let's say, 1, 1 for A, and we're going to minus this by 1, 0. So of course we know this will just give us 0, 1, just from adding, from subtracting. But now, if I were to convert this into 2's complement, well, first of all, for 1's complement, it would become 1 becomes 0, 1 plus 1 gives us 1, 0 in 2's complement. And when I take this number and I go 1, 1, 1, 0, and I add them now, well, now I'm going to get I'm going to get this. And now, since this is 2's complement, we can just cross that number out and we get the same answer. But how the hell does this actually work for this? Well, if I were to make C1, if I were to make C1 negative 1 now, just 1, this becomes 1. B0 will become um, 0. And now looking at our table, when we have a 0 and a 1, we're going to get an output of 1. Because the 1 comes in from the C. And then the value of A of A0 is going to be this number, so that's also going to be 1. So 1 plus 1 plus 1, well, that will give us 1 with a carry. 1 with a carry of 1. And then we have a 1 input here. But now you notice this B1 is not 0, it's 1 now. So we're going to have an input of 1 here. We have an input of 1 and 1. And we have 1 and 1, we're going to get an output of 0. This is going to be 0. And then A1 is going to also equal 1. So 1 plus 0 plus 1 gives us 0, the carry of 1. And remember, we cross it out, and we get 0, 1 as our output. So we've just converted B into 2's complement. All the B values were inverted, and then we added an extra 1 to compensate and change it to 2's complement. Now, if I were to make this addition, and let's make it let's make it Let's just clean this up. Okay, so if I were to now add the numbers 1, 1, and let's say 1, 1, well, that becomes 0 with a carry of 1, and that becomes 1, 1. So when I am adding, remember my x value, or which is actually my cn, well, that becomes 0. And now my b value, my b1 value is 1, and 1 plus 0 gives an output of 1. And now 0 plus 1, and then a is 1. That's going to give me 0 with a carry of 1. And then I'm going to have a 1 here, and then I'm going to have 1 and 0, because this is coming around again, and therefore my output of this is going to be 1. This is going to be 1. So 1 plus 1 plus 1 gives me 1 with a carry of 1. And there you see. This circuit will both add as an adder and a subtractor, depending on which value you plug in for your input bit. That's why back in the video about adders, I said it's also kind of important about the fact that this does have its own input carry. So that pretty much sums up adder subtractors. Thank you for your time, guys.